Hi all, and welcome to this lecture. In this lecture, we will learn how to build a deep neural network for image classification. Now this lecture will be structured a bit different. I will start by going through the slides here to the left, and as we go through the slides in the left, we're going to be building the main part of the code. A quick walkthrough of this book, of this Jupyter notebook, is it's separated into two main parts: the data pre-processing and the deep neural network part. The data pre-processing has been covered before in another lecture, so in this tutorial we're not going to go through this code. But a quick recap is we have some packages that we import here at the beginning. We import the data, so we have the data stored into two separate files, the train set and the test set. We define our classes, which are birds and not birds. In this particular case, we have 380 birds in our training set and 78 non-birds in our training set, while we have 25 birds in our test set and 13 non-birds in our test set. Of course, you can go and increase this, but for the sake of this tutorial, this should be enough, as I want to show you how to build a deep neural network from scratch and without having a lot of time on training the model and testing the model. In here we can get more information about our data, so the total number of training examples, the total number of testing examples, the height and width of each image, the size of each image, and 3 here refers to red, green, and blue. So again, it's the same numbers: 458, all shape 64 by 64. The train set Y is of course 1 and 458, which contains the labels of the training set. The test set is also 38, 64 by 64, 3, and 38 labels. Now, if this is not so clear, please take a look at my previous lectures, and hopefully that will be clear. Otherwise, just put a comment below and I'll be more than happy to help you, or others in this case. Then you reshape the data, and then you standardize the data, and then you have it ready here. So this refers to the number of features per image. So in this case, we have 12,288 features for 458 images, and the same with the test set. So as I said, we're not really looking into the data pre-processing part in this video. We're going to look more into the deep neural network part. So how do we build a deep neural network from scratch? So we're not using Keras or TensorFlow or PyTorch or Theano or anything here. We're purely using Python to build a deep neural network. So there are several steps to do this. First, we start by initializing the parameters of W and B. The second step, we do forward propagation. The third step, we compute the cost. The fourth step, we do backward propagation. The fifth step, we update the parameters and we put it all together here in the deep neural network. Then we predict on our deep neural network, and then you can import your own image to test how it's going to work. So instead of starting this way, we're going to start by putting the main function together. So let's start thinking on how do we put the main function together. So I'm just going to keep this here for now, and let's just define a function and call it our deep neural model. So what does this deep neural model need? Well, it will need the input data. We're going to call it X. It needs the output, or the actual answer, whether it's 1 or 0, whether it's a bird or not a bird. It needs the amount of layers. So how many layers do you want your neural network to have? 5 layers, 10 layers, 20 layers, is up to you. You need to define the learning rate. So let's say 0.001. Can be any learning rate. How many iterations do you want? So let's say we want 2000. And printing the cost. So as it runs, do you want it to print the cost or not? Let's initialize it with false, and then you can have it true if you want that. But if I don't want to clutter my screen, so be it. So these are the main parameters that we need in order to have a deep neural model. So let's take a look at the slide here to the left. So what do we see here? That we have the input features x1 and x2. So in our case here, we have 12,288 input features. So we need to initialize an equal amount of the weights and be the bias. So we're going to keep this one high level. So the first thing we have to do is we need to initialize our parameters. So we're just going to put in parameters, taking in the amount of layers. So here's your layers. So if we just see here, so it's super, it's more clear. So if here are your layers, you want, if you provide in 5 layers or 6 layers or 7 layers, you want this function to be able to create the amount of random weights that you need. So that's the first thing you want to do. What happens after initializing your parameters? Well, you want to start with your forward propagation. Let's just put in a for loop, and this for loop here is how many times do you want to have a forward propagation and a backward propagation. So one loop is one forward and backward propagation. So basically we specify the number of iterations as 2000. So we want 2000 iterations. We want 2000 forward propagation and 2000 backward propagation. So let's just put this as a cap. And we at the end of the product of the forward propagation. So let's call this model forward. So what do we need in order to calculate the forward propagation? Let's do this. So what do we need in order to calculate the forward propagation? Let's take a look on what we have here. Well, we need the x. Definitely, we need x. So as you can see here, w1 x1 plus w2 x2 plus b. And what this is showing right here is you have only 2 input features, so therefore you have 2 weights and a bias. In our case, we have 12,000. So it's very important that we get the amount of x in order to know how many weights are we calculating. And then we need the parameters, and the parameters is basically how many neurons are there that we've calculated earlier from here. So the output of this will be the end here, and that will be two values, which is your AL and your cache. So of course we have an indentation problem here. Yeah. So what you see here is actually a single neuron, not a deep neural net or deep learning or anything. I just wanted to show you this to oversimplify it a bit, so it's clearer. To see. So it takes an X and it takes in the parameters. Well, someone can turn around and tell me, oh, but what about the activation function? In the model forward, we're gonna define the activation function. So after we calculate the forward propagation, we need to compute the cost. So this is another simplified diagram of the previous lecture. So we have several input features, and then we calculate the Z, and then we calculate the activation function, and the activation function is the output. In our case here, it's AL, which is the y hat. It's the answer what the neuron thing it is, versus what it is actually is. So y hat here is what the neuron thinks it is. But again, this is just a single neuron, and I use this to simplify the idea. So after you calculate your forward propagation, the next step to do is to calculate the costs. So again, it will be simply, let's call it compute costs, and it's going to take in AL and Y. So Y is the actual answer, and AL here is the Y hat, which was the last activation from the last neuron. And this is how it's calculated. Again, we won't implement it here. We're going to define compute cost here. So we got the cost. After we have the costs, then we need to calculate the back propagation. So here is the back propagation, and I'm doing 2 things here, the back propagation and updating the parameter. So this diagram has evolved a little bit, going from a single neuron to 2 neurons. So again, we have our input features, and then we got WT, which is the weights, and B is the bias, and A is the X actually. So A equals X in this first. I'm actually seeing it now. So A is X, and this is going to be actually 2 now that I oops, sorry. Yeah, this is going to be, that's correct. So you calculate the weights and you calculate the bias to get Z, and from Z you put it on a sigmoid. This is a sigmoid, but we're going to use a ReLU. You can use ReLU, 10H, whatever. This is just for demonstration purposes, and you then have the activation. you pass on the activation to the next neuron, and then you calculate y hat. So the back propagation, which is what we're trying to calculate here, let's call this model backward. And model backward, which is the back propagation in this case, takes in the AL, which is the value you've calculated from the forward propagation. You're gonna take in y, which was the actual answer, which you also needed to calculate the cost, and caches. And what are caches? Caches is basically gonna be the output from the model forward, which is the values z, a, and w. Z as in the weights that you needed right here, and W, which is the weights you calculated, and B and A. And you need these values in order to calculate the derivative of these following values. And when you calculate these derivatives, you then go and update your parameters. So let's write that now. Let's call it parameters. We can update our parameters, and we basically, it's a typo right there. Let me fix it. So basically, we have the parameters, and it takes in the parameters that has already been passed on earlier. So the first time it will be whatever weights they were. Then you got the gradient descent, which you calculated from the back propagation, and the learning rate. And these are the update parameters equations. We can also, if the user would like to print the cost, so let's say we just do this, if the print cost happens to be true, then the user can get an output of the values, which is just right here. I'm not going to go through this one, but it's pretty straightforward, as you can see, and the plotting code. Again, I'm not going to go through the plotting codes. Since we're focused on deep neural networks now, not how to plot MATLAB graphs. Okay, so to quickly summarize or recap, to build a neural network, we need these 5 essential steps, which we initialize our parameters, we calculate the forward propagation, we compute the cost, we calculate the backward propagation, get the gradient descent values, and update our parameters. The rest here is just for convenience of the user. So in order to make this work, let's just say parameters, and we're gonna call our deep neural network. So it will take in the training value X, is gonna take the training value Y, it's gonna take the amount of layers you would like it to be, how many iterations. So the iterations already defined as 2000, and the print cost. Well, you know what, let's take a look at the print cost, why not? So these are already defined, so you don't have to really redefine it unless you wanted a different value. And when you execute this, it should then print the graph that you want. But for now, we have set the skeleton and the steps, and now let's go and create each function. Let's create the initialize parameters, deep function, let's create the model forward function, let's create the compute cost, so on and so forth. Before we jump into that, what we can say, how we can already start thinking how many layers. Let's say we're going to create a 4-layer model. So the first layer must have 12,288 neurons, since that corresponds to the amount of input from the images. We can say we would like the next one to have 20, the third one to have 10, the fourth one to have 7 or 8, and the last one to have 1. Well, it's the output. You want to get an answer. Give me an answer. So let's start with the initialization parameters deep. So let's go here and define a function. We'll call it initialize parameter deep, and that function will take in the layer dem, which is the amount of layers that you would like. Let's create an empty dictionary, call it parameters, and let's get the actual length of the layer. And now let's for loop. I'm going to speed this up a bit. So what we have here is for the length 1 to 5 in our case, we want to initialize random values, and these random values for the weights shouldn't be 0. but you can have zeros for the bias. We have covered this, so this is the size of your matrix parameters, and this is the amount that it's gonna be creating. So in the first layer, since you're starting here, it will be 12. This one here will be 12,200-88, and then where was the values? 20. And this will be 20. Again, we covered this in the previous lectures, so this is how we would initialize a deep neural network parameter. So let's return the parameters, and there shouldn't be a problem here. Next, let's calculate forward propagation. Before we go into forward propagation, the parameters here will contain a Python dictionary, since we created the dictionary here. So it will contain a Python dictionary containing the parameters of W1, W2, W3, W4 of all the layers and the bias vector. So this is what the parameter will include here, and here it will have the values of 0, 1, 2, 3, 4, so on and so forth. So a bunch of random values are going to come out of here. Let's show an example. So let's do this. Let's take this, and let's say we have 3 input or 2. Let's look at here. So let's say we have 2, and you want 3, 5, 1. There we go. So what do we have here? So we have W1 has 2 neurons right there. Where's W? Oh yeah, sorry. So there is W1. It has the weights for W1. So there is the weights for W1. There we are, and there we are, and there is your B1, which also matches. It's 3 by 1 because these are 3. So if you look at the matrix here, so that's your value 3. So you got neuron 1, neuron 2, neuron 3, and that couples with the feature, and that's why here's 2. So if we up this to 3, then you got 3, because the amount of the weight should be the same as the number of input features. So if this is 1, then that will simply be 1, because you have 1 feature, therefore you want 1 W1, and 3 neurons, because you have identified 3 neurons here. So if you want 2 neurons, you got 2 neurons. Same with the B1, and then you got W2, which is the second layer, and W3, which is the third layer. And then this is your output layer. So this was just a quick demonstration. Now let's calculate the forward propagation. So model forward, I think that's what we called it. So if we look down here, we have our model forward, and model forward takes in X and the parameters. So what does X mean here? X is basically the data, the input size, and the parameters is the output of the initialized parameters. So it takes in the random values here. So let's go in here. So let's look at this one. So the forward propagation takes in the X and the W values, and then it calculates Z and the activation function. So let's create caches first, and basically, as I explained earlier, caches, it stores your values, and when it stores your values, it will be able to calculate the back propagation, because you have all your forward propagation from all your neurons stored. And in the first round, A equal X, and I think you've seen me when I fixed that error here. So in the first round, A equals X, but then that value gets updated. So, and what's our L? And this will dictate how many loops do we need. So the deeper your neural network, then the more loops it should do to calculate the forward propagation. So now we got our length ready, and now let's start for I in range 1L. We can start with having the A per A, and this is demonstrated if we had more neurons, basically. So in the first round, A here becomes your A previous, and when you calculate the new A, it becomes your A previous. So you keep on updating the values depending on the length of your parameters. So the first step now, let's go back here, is to calculate Z. So Z equal MP dot, let me speed this up a little bit. So we have we calculate the value of the linear equation as values. We use numpy dot and W with whatever it was. L here will be first layer, second layer, third layer, and A previous is basically the previous layer. So the previous layer in our case here was X plus the bias. So then what is in the second iteration, A previous actually is going to be the new A. So therefore the new A has to be outputted. So in our case, we're going to use a ReLU. And the equation of ReLU is quite simple, is NP maximum 0 z. So that's already in the NumPy array. So then we calculate the new value of A, and the new value of A is now stored as A previous, and then A previous is here. So now you can stack several neurons calculating the forward propagation this way. But as mentioned, we want to store all these values, so we can simply create a variable called linear cache, and our linear cache is going to save this A previous. It's going to save, well, we can just copy this because I want to save these. I can see I missed something here. Or no, actually I didn't because I closed it earlier. There we go. We don't want to add anything. So something doesn't add up. That looks much better. Yeah. So we want to save these values, and now we can close it. Let's see. Let's create a cache, and in our cache we're gonna save this and the value z, and we created an empty list here, so we're gonna append our cache to our caches, so then we can always have this as the last thing it does. Right, that looks a bit neater now. So this is basically how we calculate our forward propagation. But what if you wanted to have separate forward propagation? So in this neuron, you would like to have a ReLU, and in this neuron, you would like to have a sigmoid. Well, then it can calculate the ReLU several times here, because A here is in a ReLU, and you want only one sigmoid, and that's explained in the previous lecture. We would prefer, if you have a binary choice, is to simply use a sigmoid. And to have a sigmoid at the end is that you just exit the for loop and actually just re-implement everything again. So if you just let's copy these values here. So let's just take this. Well, we don't care. So let's just do this one, and let's make sure it's outside the for loop. So it's this way, and then we would like our L, which is the last one, last layer, to be responsible of this. And in this case, we had a ReLU, and let's put a sigmoid. And the equation of a sigmoid is as follows. It's just math, no magic. Well, math is magic. So we got this, and again, we want to save our linear cache. Let's make sure that we want to save those last values also. So let's do it that way. Let's call this AL in our case. Since this is the last layer, we want to differentiate that this is the last activation layer, and let's save our linear cache in Z. And now we want to return the AL and the caches. Okay, so now we have actually calculated our forward propagation. Next, compute costs. Where are you? There you are. So let's calculate the compute cost. So what did we have here? So the compute cost takes two things, the AL and the Y. So AL, which was the last value, and Y, which is the actual answer. So let's define that. And we put it right here. This is the loss function for a single. This is the loss function. What we're going to calculate is the cost function. So the cost function is basically 1 over m, the sum of all of this, because you want to calculate the average over your whole data, and that is something you would get from here. So y.shape1 basically means y.shape1 should basically mean your actual answer length. So that is calculated from the total 458. So basically it's this one here. That's your 458. And these are your total number of examples. Actually, you could have chosen X, it doesn't matter. So how do we calculate that? I'm going to copy paste the equation since it's a bit long to write. So let's just do this. So here is the equation. The only difference is we sum it up across all the examples and divide by the total, but the inner part here is just this equation here. Let's squeeze it to remove any unnecessary dimensions. So this basically makes sure removes any unnecessary dimensions to not cause any problems. You can read more about it in the documentation. And voila, we now have our compute cost. Next, this part is going to be a bit long since it will be a lot of derivatives to calculate. So that's why I have 3 boxes here. So let's start with a smaller example and then build to the main example. So we're going to define first the linear backward, which takes in dz and the cache. So basically the value dz, which should be here, which is the value you calculate from dA. So the first thing actually calculate is the dz value, which is missing right here. Yeah. So the same for this one also, you need the dz there. Okay. Okay, so let's just do this for now. So you need to calculate the linear backward first, then we need to calculate the linear backward activation, which takes in the activation, the cache, and the actual activation. So what activation was there? And you can see here we had 2 different activations in our case. We had the ReLU and we had the sigmoid, so it has to be identified. And then finally we put the actual back propagation together. So the model forward was quite easy, but the model backwards is a bit longer. So we then have the model backward, which will then take the AL, which is the final one, your final output. It takes in Y, which is the actual answer, and it takes in caches, which is all the values stored. So by having all these values, you should be able to calculate the backward model. Let's fix this. Okay, so these are the 3 things you need. Let us start with the simplest one, or the first one is not simple, which is the linear backward. So what does the linear backward do? It basically implements a linear portion of the backward propagation for a single layer. So it calculates the portion for a single layer. It takes in 2 arguments, the dz, which is the gradient of the cost with respect to the linear output, and the cache, which is a tuple value of the previous activation value, w, and b, coming from the forward propagation in the current layer. And that's why we needed the cache to store the values so you're able to calculate. So you need to store z and a and w and b in order to calculate these values, and these values is the slope, the change, which you would need to update your value w right here. So let's start. So the first thing you want to do is extract the previous activation, the w and the b from your cache, because these must be at this point stored at your cache. So let's go down here, and then you need, of course, the m value, and these are derivatives that we have demonstrated in the previous lectures. So let's do this, and let's see if I remember how to use the keyboard. So we're going to do this, shape 1. So we need to calculate dw, we need to calculate db, and we need to calculate the new activation function. Well, sorry, not the new activation function, but the next previous, the derivative of the activation function. I think that's a better way to put it. So how do we calculate dw? Well, there is an equation for that. So I'm just gonna put it right here. So this is how you calculate the value dw, and it uses dz, a, previous, and it's transposed. So you can, where did it get this dz from? Yeah, you actually pass it. So the linear backward is passed right here, and this dz will be passed from function in the activation. But for now, let's just continue with this, and I'm gonna explain it again when we finish the other two functions. The dB is calculated on this by using this equation, and dA is calculated this way. So if you're interested, you can Google the derivatives of a backward propagation, but otherwise these are just the equations. And you can see by having the DZ value and by having the caches saved, which is the A prev W and B, you can calculate the derivatives of the rest here. Next, the linear activation function, and let's not forget to actually return all of these. So can you return this please, and that one please. Thank you. So what's the linear backward, and then what's the linear backward activation? Basically, the linear backward activation is applying the activation function to this, since we had two different activations. So it takes in three arguments: dA, which is the post-activation gradient for the current layer; cache, which again contains a tuple values of the computational values that we just had here, and the activation in our case if it's a sigmoid or ReLU. This will return the gradient of the cost with respect to the activation of the previous layer. It will also return the gradient of the cost with respect to W and the gradient of the cost with respect to B. So these will return all these values. So again, if we just make it clear here, so we're gonna return again the same, but with the actual activation function applied to. That's all. That's the difference. So we create an if function. So if the activation is a ReLU, then this is, again, I'm just putting in the equations. This is just converting the DZ to the correct shape. So let's just get it right. And then if the activate, let me just again copy this so it's much faster. This is the equation for the ReLU, and right. So this is if it was a ReLU. I'm gonna explain it in a sec. Let me just finish. Else, if the activation is a sigmoid, let me go speed this up a bit. And this is the equation if it's a sigmoid. Again, this and the actual contents of the equation is just linear math. It's nothing to do with programming. So these are just converting the mathematical equations into code here. So what is exactly happening here? Well, we can just divide this into two parts, so it's perhaps easier to see. So in this first part here, we're calculating DZ, which is the ReLU, based on the activation passed. So based on this dA value, we have calculated the slope for Z. And by having the slope of Z with your linear cache, and remember your linear cache here is the values of A, W, and B, we're able to derive dW, dB, and dA. So let me try this again for the sigmoid. So again, by having the value of the cache, so in this case, to calculate sigmoid, you needed the cache. So cache 1 and cache 0. So in this will be also clearer later. So cache 1 contains the values of A, prev, W, and B. We get S, and by having S and having the activation dA from here, we're calculating dZ. And then we're calling in the linear backward to calculate the rest over values, and we're returning these values. So basically, this function here is just applying the activation over this. I hope this was a bit clear. It's a bit confusing, but I hope it was clear. So now that we have all these values, let's put it together in a big model. And this model is the model backward. So it takes an AL, which you have figured out is the first time, it's the last value, or it's the y hat value in our case, which is AL. We also call it y hat. We refer this to the last activation function in a neural network. And then it takes in y, which is the true label vector, while AL is the probability vector of the whole forward propagation, and the caches is basically every single forward value. So all the values we calculated here from our forward function is stored in this here, and this is then used as an input to calculate the rest of our values. Okay, so let's create a dictionary and call it grads, in our case the gradient descent values. It takes in the actual and the L, it could have been Y, doesn't matter. It takes in the total number of examples, and you want to make sure you have this reshaped properly. And I can print out so I can show you guys. Okay, so these are just like initial things we have to do to get it all in the right mix. And this line basically guarantees that Y is in the same shape as AL and it doesn't have any like weird things coming out of nowhere. So let's calculate dA. So we have AL and we're going to calculate its derivative dAL. Again, this is an equation straight from the literature. And this is how it works. So to calculate the derivative of AL, which is the back from here, you need two things. You need Y, which was the actual answer, and AL, which was the probability. And by applying this, you calculate the derivative of AL. Now, let me try to explain this. So our deep neural network starts with creating an L amount of ReLU. And then the last layer is a sigmoid. So we got several layers of ReLU, and the last layer is sigmoid. So if we can imagine this, so let's say G is a ReLU in our case. So we have several of these, n amount of these, and then the last layer is the sigmoid function. So when you do the back propagation, you start with the sigmoid function and then you do the for loop for the actual ReLU. So that's what we're going to start doing here, is that we're going to start with calculating the derivative of the sigmoid function, because we're going now this way. So we're going to simply need two things. So we need the current cache. We need to calculate the current cache, and the current cache is all stored in the linear backward activation. So we're going to put in here, and we're going to basically pass this DAL as in here. So since this is the last layer, you're trying to calculate this. So that's DAL. Maybe, oh, should have done it earlier in the video. So you can now start seeing the code more. So we're going to calculate DAL right there. And next we're going to take in the cache. So whatever cache we want to have the previous values. So we have L. Have we calculated L? Let me see. Okay, so we forgot L, because how else would you know how long is it? So get me the length. So if the length is 5, then I need the caches from the 4th layer. So I need the caches from the 4th, not the 5th, because the 5th will be here, which is non-existing. So we need this one right there. So let's continue, and then we know it's a sigmoid. So the linear backward activation right there. So it takes in the last layer, the cache's value, which is the Z, A, W, B, which are all the values you need in order to calculate your derivatives, and then the activation if it's a sigmoid or ReLU, and the first one is a sigmoid, so it's going to go straight here. And the output of this is going to be 3 values, which is the DA, 3 variables, sorry, not values, variables. It's going to be a matrix, and it's going to have a lot of other values. So we can simply expand this to as follows. I'm going to speed this up. All right, just quickly written up. So basically, it's going to make sure that it's storing the value of DA in the right layer, the value of DW in the right layer, and the value of the bias in the right layer. We can also do this and paste it here, but just for readability. So now we have the sigmoid done. Now we can create a for loop, and this for loop is going to calculate all the values that have been in the ReLU. So we just do this. Again, we will actually, it will be exactly the same. So So just we're gonna take we need the current cache, and it's calculated for linear backward. But you're not gonna take it from the DAL. You're gonna take it from the last one right here. So let's just do this. And of course, it's not L in our case. It's gonna be L, and you want to go +1 to make sure you got the right ones. Again, now your cache is L minus 1. This is, again will be L. So just for the current layer. So you want to calculate it for the exact current layer in our case. So you're going in reverse, basically. To better demonstrate this, let me show you the output. Oops. Wrong. It's reversed. Okay, so let me show you. So let's say L is 5. We do this. Do this. So we see here, if you have 5, it starts from 3. Therefore, you want the value of the 4th, which is right before the end. And you need the values of the 3rd layer for your caches, which is right here, in order to calculate this. So I hope that makes sense. So you need the activation layer of this and the values stored in here in order to calculate these values, because obviously the values will not exist from here. So therefore you need to get the ones from this layer. I hope that clears it out. So we calculate the current cache, and of course it's not a sigmoid in this case, it's ReLU. So we need the F function up there to find that it's a ReLU. And then we need to, well, we have several ways. So now we have the current cache, so we can also do it this way. We extract all the values individually, and then we store it. We want to store it in the right place. So let me fast forward through this. Okay, just fast forward it. So we have the current cache, which is this one right here. Again, it's the same as this. It returns the DA, the DW, and the DB, but we have to make sure that each is stored in the right location. This is just again for readability, but you can do the same as the above. You can also do this and this, just to show you the different ways of doing things. And we just return our dictionary. Return, and just make sure a bit back here. Okay, now we have all these values. Last is update the parameters. You want to update the parameters with the new values. So what do we have in our update parameters here? Let's see. Let's define it. It takes in the parameters, obviously, since you need the parameters, which is the equations right here, the W and the B, the bias, the learning rate, which is that one right here. Let me just make this big. So, and the gradients. So you have the parameters, the learning rate, and the grade or the derivative right there. And then this gives you a new weight and a new bias. So you began with actually randomly initializing it, but now you're actually calculating it. Oops. Right, let's make this big now since we have the idea. Where is that? Yeah, right there. There we were. So you want the length to start with. And then you want to for loop on all your layers, on update all your W's, all your weights, all your biases. So this is simply going to be the equation. So I'm just going to fast forward through this. Okay, just read it up. So here we see for the layer 1, just ensuring all the numbers is the same here. What you want to do is get the learning rate and times that by the gradient of the slope. So basically we just rewritten these equations here. So the moment of truth, or shall I say the moment of bugs, let's restart and run, and it never works from the first time. But let's see. Let's see what our bugs are now and fix it. Syntax error, else activation equal sigmoid. What did we do wrong here? Well, there's no such thing as else, it's elif. But I also realized something is I haven't actually expanded my cache. And this is where the values activation cache comes into play, and the linear cache. So I apologize about this. So the cache expands to the linear cache and the activation cache. And the value of cache here from the linear activation function comes from here. It's passed originally from here, and the activation cache is actually the value of z, this one right here, and the linear cache is the value, or is the other parameters, the weights and the biases. And for the ReLU here, that's why if the activation function is less than 0, then it will be 0. It's not a leaky ReLU. So we saw that. Let's see now. Okay, layer dims is not defined. I added it right there. Did I misspell something? I can already see it. Layers. It's right there. Next, name L is not defined. Yeah, probably should have been capital. Right, because I put it as I. It's crazy how you miss all these things. Next, shapes. That is actually a very silly mistake right here. You see, it's actually almost two mistakes. The first mistake is that the linear cache here can't be the last. A-priv is it's not here, so basically it has to be A. It has to be the last value. So we're starting with that. Second mistake is, where did this come from? Now let's take a look. Again, same problem. Let me take a look. I can already see that it's here. Should be A, which is the last value, and not more errors. Too many values to unpack. Well, this is gonna be fun. It's basically complaining about the cache. There's too many values, so some value. So it's basically saying if this is 1 or 2, it's missing B or missing W. So let's take a look. Okay, so there are a few things to fix here. First of all, I noticed that I haven't defined costs. So let's define costs as an empty bracket to keep all the to store all the values for the costs. I also realized that I haven't divided the parameters by 2, because I remember I have done that somewhere earlier with the parameters. Yeah, in the model forward. So let's restart and run all and see if it persists. Okay, it persists. So something's up in the model forward. That's the only explanation. It's right there. Let's try now. Okay, we have something. Cost after iteration 0, cost after iteration 100. So it's now gonna keep on working. We had 2000 iterations. That's 200, 300. If your PC is really, really slow, then just reduce the amount of iterations. I'm gonna fast forward here. I'm actually quite guessing that it's really small here. I'm gonna actually increase the learning rate and see. Let's see, it just looks a bit small. Let's try with this. Or actually, let's increase it even bigger. Let's do it this way. Just guessing. Let's see. I'll come back when it's finished. But it should be a bigger drop now, because I could see it's changing very lightly. Yeah, it's a much bigger drop now. I'll be back. So hi again. Now it's finished, and we can see that the cost has been reduced, and you get a graph, and you can see it's not going any lower than this. So now we can calculate the prediction on this. So I'm gonna fast forward into writing this one. This is a function to calculate the prediction. So we can predict what's our accuracy on the training data. So here is the accuracy of our training data and the accuracy on the test data. So we can see we just call in predict, and we pass in our train X and our train Y along with the parameters, and the parameters are the last parameters we calculated from our model, and we've converted it into 0 and 1 prediction, and it's the same, and this is how we have it here. In the previous lecture I explained actually how do you have your own image ready, so I'll simply just copy the code here, and I already have an image stored here. So I run this, and basically you can see the accuracy is 1, which is basically it managed to predict that there is a bird in this picture. So I hope you have gotten something out of this. If you have any questions, please don't hesitate to post it in the comments section below. Thank you.